Hopefully everyone on Zoom can hear us too. Very delighted today to introduce our speaker, Dr. Evi Micha, an assistant professor at USC and a leading expert in the section of computer science and economics, focusing on computational social choice and algorithmic fairness. And notably, her research has received significant academic recognition, including the 2024 Best Dissertation Award and selection as exemplary in the blind modeling track of ACM-EC in 2023. So today she will present her work toward pluralistic alignment from axiomatic approach to pairwise calibration, offering directly robust methods to design ensemble-based rewards that preserve the full diversity of human values. So yeah, please join me in giving full welcome to Dr. Micha. She's welcome to receive clarification questions during the presentation, but for like more in-depth questions, we'll up until the end of the presentation.
Yeah, thank you very much, David, for the kind introduction, and thank you for also this invite. I'm very happy to be here. So yeah, as David said, I'm a new assistant professor at USC. I'm downtown, and I'm very excited to also visit eventually ISI. So it's my first time to be here, and I'm very excited about this. So yeah, as David said, today we'll talk about pluralistic alignment. And before we dive into this and what is AI alignment and how we can achieve some pluralistic alignment, I would like to give a brief overview of what I'm working on. So I'm working on the field that is known as computational social choice. So social choice is a field that is at the which is a very old field from economics, and computational social choice is actually at the intersection of economics and computer science. So questions from social choice, which means how when people have heterogeneous preferences, we make collective decisions about them, we see them from computation lens in this field. And it has many real-life applications. For example, how do we make decisions for social good when we have scarce resources and we want to allocate scarce resources to different people that have different needs or utilities or preferences that we want to take into account. And has many other applications like voting and general fair division. And nowadays, in particular, with respect to voting, there are many applications related to civic participation and how we can really increase civic participation in our current democratic system and how we do this from an axiomatic approach. So this is one lane of my research, and one thread of my research. Another thread of my research is algorithmic fairness and AI alignment. And here I'm focusing on fairness in different machine problems like clustering, multi-embodied, classification, and so on. And also on pluralistic alignment, which is how we really make our AI algorithms or our machine learning algorithms to be aligned with human values. And in general, what I'm trying to do is to get axiomatic approaches or notions of fairness from the field of social choice and apply them into different machine learning applications, and especially in applications with multiple agents, because the field of economics and social choice theory especially focuses on when we have people that have different preferences, on when they are strategic, and essentially nowadays we have many multi-agent systems, and so ideas from social choice, very nice, and economics in general, very nice applying different machine learning and AI problems. So that's the main overview of what I'm working on, but today we'll talk about AI alignment. And so before we dive into more into this field, I would like to give an idea of what is AI alignment. So this is just a definition that I got from Wikipedia. There are many, many different definitions that someone can come with. So economists have tried to come with a very rigorous definitions of what is AI alignment. Philosophers have also tried. So here I'm just going to give a very abstract definition, which is we just want to make our systems to work the way that we want them to work. So we don't want just an AI system to do something that is not desirable for the society. However, today we will mainly focus on what is desirable for the society and what does it mean that something is desirable. So in general, how people try to achieve in AI alignment. So there are different techniques, but when we're talking about for LLMs and all the modern technology, I think the way to go approach usually is this idea of reinforcement learning with human feedback. So what is this idea? Here we assume, so I will just give the example using LLMs, but you can imagine that here you have AI model or you want to achieve everything, anything. But I'm just, as an example, I'm using LLMs. So how do we train LLM? Usually we use tons of data that we have available on the internet. And then we have an AI model that we train, probably it is some deep learning algorithm or some technology that for now we'll just use it as a black box. And then given the training that we have done, what we want is whenever a user asks a prompt to an LLM, then the LLM outputs an answer for the user. So this is what is known as the pre-training AI model. However, because in general, oops, it's this way. Because in general, we want to ensure that the output is safe, is robust, is fair. So we want to ensure that whatever our AI model does is good for the society. Usually, we don't just do this pre-training and then we just use this AI model as a black box. But instead, we try to ensure that the output has some nice properties. And so the usual way to do that by this idea of reinforcement learning with human feedback is that given the output, you try to also incorporate a reward function and then to do some filtering and deciding what is the output that you actually give to the user. And so essentially the reward function here tries to ensure that outputs that have high reward, which means that have some nice properties that we want, are the ones that we actually output to the user. So there exists this pre-trained model, there exists this reward function. So in general, a reward function can be a very complicated model, can be neural network itself. But because I'm working on theory, we're going to simplify things a little bit here, and we're going to make the standard assumption in theoretical works that this reward function is actually a linear model. So this means that for each pair of prompts and answers, we have some embedding, and then given the embedding of this pair, what is the reward for this particular pair? It is their dot product with some parameter vector theta that we try to learn. And so what is known is the embedding, and what we try to learn here, what we try to design in an desirable way is this parameter vector theta.
I have a question
Yes.
about this framing. So you're saying that you have a reward for each prompt answer pair.
Yes.
Is this a way to mimic the reinforcement learning setting where you have a reward for each state action pair?
Yeah, I think it is kind of similar here. So it is like in Markov decision process, usually you have for each state an action, a reward. So yeah, this is kind of similar. Yeah,
Okay.
yeah. It is like for prompt and answer. Yeah. Yeah. So this is, as I said, in practice, it's not necessarily that people go with linear rewards. However, in theoretical works, people usually focus on those because it is easy to generalize, because what we want to learn here is want to be generalizable for prompts and answers that we haven't seen, and so on. So it is a very, very common assumption. And now where the reinforcement learning part comes into play, so usually as you learn this reward function, usually you also have this reinforcement again, where you try to fine tune your LLM using this reward function. So you don't want just to have to be this completely separately, but you use these rewards to also fine tune your model. Okay, so as I said, how you pre-train your model, how you fine tune your model, it is a black box for us in this talk, and we will focus on how we're going to design the reward function here. So how are we going to learn this parameter vector theta that has some nice properties. And so how do people design this reward function in practice? This is where human feedback now comes into play, where essentially you ask the different humans what are their preferences over two different outputs, A or B. So for example, if you think about ChatGPT, in many cases, you see two different answers, and ChatGPT asks you to choose which one you prefer. So essentially, ChatGPT and any LLM tries to get your feedback at this point on which answer is best. And so here you have humans, and each human just report their own preferences. And this is how, and essentially the problem of reinforcement learning with human feedback is how, given these preferences, how given these Pairwise comparisons in this particular case, A versus B, you decide how you choose this parameter vector theta, which corresponds to a reward function that you want to learn. Okay. Any questions about the basic model? Because this is where we're going to build so far. So yeah, essentially, you don't need to remember the whole picture. I think what we want really to focus on this talk is how, given the feedback, we are going to design this linear reward model. Okay, so how do people do this in practice? So usually they assume that the preferences that they see from the users come from a random utility model. So what this means that there exists a ground truth answer. For example, A is better than B. And what you see, the responses of their users are actually noisy estimations of this underlying ground truth. And there are different utility models that people have defined in theory, but I think the one that people actually use in practice is the known Bradley-Terry model, where essentially here you assume that there exists an underlying reward function that you don't know. And so for each answer B and prompt, for each prompt and answer A or B, you have an underlying reward that you don't know. But what you observe is that what is the probability someone to tell A versus B is essentially proportional to the exponential of these rewards. Why exponential? This is how Bradley-Terry is defined. Someone can also just use proportional of reward of A versus reward of B, and so on. But this is the most common model, and this is what people actually do in practice, to the best of my knowledge. Okay, so when you assume that you have this underlying distribution, so we don't know what is the underlying reward, but what we observe is I will learn that it should be done. Okay. What you observe essentially is that you ask random people to prepare A or B, and then they draw from this underlying random utility model, and this is what you observe, A versus B. Okay, and when you have this, the assumption that this is the model, this is the underlying model that you have, what you try to do is that if here I denote with this pi the profile of ordinal of preferences in general, can be pairwise comparisons or can be even ordinal over all the whole number over all the different options. So essentially what they try to do is that, assuming that this is the underlying random utility model, they try to find the parameter vector theta that is the maximum likelihood estimator versus what they have observed. So yeah, you don't need to go on this equation, just believe me that this is essentially the maximum likelihood estimator by assuming that we have the Bradley-Terry model as a random utility model. So, and essentially this is what people try to do is that, okay, they observe some preferences and then they try to find, to fit this reward model that is the most probable to be the correct model given what we have observed. This is what maximum likelihood estimator means. Okay. Okay, yes.
I have a question.
I have a question.
Yeah.
So is this for one prompt, you can have answers A and B and you're choosing?
Yes.
Is it possible to have more than 2 answers?
In general, yes. And actually what we are going to discuss today can be generalized even if you have like a full ranking over the different candidates. Yes. And actually, even this model, so I'm having this Bradley-Luce model. So Bradley-Terry model is for pairwise comparisons, where you define it this way, but there exists an extension which is called Bradley-Terry-Luce model, which essentially takes into account the whole ranking. It is a similar formula that just extends to rankings. And again, you can do maximum likelihood estimator and learn based on this. Okay, so essentially so far what I have mentioned to you is that there exists another underlying ground truth, which we don't know, and we try to learn by getting human feedback. However, today I want to focus on pluralistic alignment, and I want to get away the assumption that actually there exists an underlying ground truth. What we see is noise estimations, and we just try to approximate the underlying ground truth. But instead, I'm claiming that in some cases, people have really heterogeneous preferences. And so really what you try to learn is not a ground truth, but somehow you try to learn a reward model that is good for all of them. So essentially here you want to make some collective decision. And so how we're going to model this here is that we're going to assume that there exists no another line vector theta, for example, that corresponds to this linear model that we don't know and we try to learn. But instead, each agent has their own parameter vector theta 1 to theta n, which essentially this corresponds to a full ranking that they have over the different candidates, where the full ranking can be just induced by in a decreasing order of the rewards over the different options. And now the question is that given these heterogeneous preferences, and even if we assume that we have perfect access to these ordinal preferences, the question is, how do we really aggregate these preferences and how do we really design a reward function that is good for the whole society? So the first thing for doing AI alignment is to decide, given the heterogeneous preferences, what does it mean that we get a good decision for all of those? Yes.
What does it mean this is like good for society?
I'm going to define this very rigorously. So yeah, this is where exactly ideas from social choice come into place, because social choice actually has studied this problem for centuries, since 12th century or so, where essentially you say, okay, I have people with heterogeneous preferences, how I'm going to aggregate them in a way that I have some good properties. And what good properties means is where the axiomatic analysis come into place, where essentially you want to ensure that you have some good properties, some nice actions, which means that if this is my input, I want my output to have this property. And we're going to define all of those very rigorously, but as I said, this is essentially, if you think about this, it's a classic voting scenario. Yes.
So I have a question. So if there are multiple values involved in this decision making, so if the human's valued order is prefer A over B over C, so how will you define the level of alignment for the model? So if the model is ACB, is it aligned or not aligned?
Yes, so we're going to define all of those very rigorously. So yeah, for example, this might correspond that everybody says that my optimal ranking is ABC. If the output is ACB, is this aligned? We're going to give very rigorous answers whether this can be considered aligned or not. Any other questions? Okay. So let me, okay, yes, would be this one. So I will start with the axiomatic approach for this case, where axiomatic approach exactly, I'm going to give some rigorous definitions on what is considered that an output has some nice properties. So an output reward function has some nice properties given the input reward functions. And this is joint work with these amazing collaborators. And this was a paper that was accepted last year at New Rips, and I think it got some spotlight recognition. Okay, so let's go back to the model. And so we have these heterogeneous preferences. So we have people that have different rankings. And as I said, our problem here now is that given these heterogeneous preferences, how do we select a parameter vector theta star that has some good properties? And so to some extent, you can imagine that this parameter vector theta star, it uses also a ranking over the different candidates, because by just rank the different candidates, the different alternative options, in a decreasing order of the rewards, we have a full ranking over the different candidates. So to some extent, as I said, this is a very, very classic problem in voting theory. So voting theory started at least since 12th century, and people have studied extensively how, given input rankings, you design an output ranking. And there are infinitely many voting rules that someone can come with. And for example, one very famous voting rule is plurality voting rule, which says that I'm just looking at the top choice of the different voters. Each candidate that appears as the first choice of some voter gets score 1. Then I just sum the scores of the different voters, and then I can just rank the different candidates in a decreasing order of their plurality score. So that's just, just looking at the top choices. And there are many, many different rules. Probably you have heard about plurality, Borda scoring rule, that in Borda you just assign m scores to m points to the first choice, m minus 1 to the second one, and so on, if we assume we have m different candidates. And then again, you can rank the different candidates in a decreasing order over the different, in the decreasing order of the scores. And so why would someone want to use a voting rule from social choice theory? Because there are people who have studied for each voting rule what are the properties that satisfies. For example, a very famous property is that if the majority of people prefer a particular candidate, so they have as their top choice, then this would be the candidate that is ranked first at this position. That's one property. Another property that people have defined is that whenever everybody agrees that A is a better choice than B, then A should be above B. So back to your example, if everybody agrees that A is better than B, is better than C, but the model outputs A, C, or B, this doesn't have this property that is known as parity optimality, because even though everybody agrees that B is better than C, our reward model outputs C is better than B. So in that sense, from an axiomatic analysis, it violates this natural property that no voting group violates. So this is not a desirable output. It's not a desirable reward function. Of course, in social choice theory, it is known that there are impossibility results. So it is known that you cannot satisfy all the natural axioms that someone can come with concurrently. So this is the famous Arrow's theorem possibility, where Arrow's shows that, okay, if you want to have property A, property B, and property 3, there's no voting rule that satisfies all these properties concurrently. So we already know that we cannot do all of those concurrently, but it's still the question, okay, what can we do? And what the approaches that are used in practice, what properties violate, and whether these properties are important. So this is what we're going to discuss today, essentially. The approaches that people apply in practice, do they satisfy some nice axioms from social choice theory? And if the answer is no, can we design better approaches that satisfy some nice axioms? And hopefully all of this will be clearer soon. However, I want also to insist a little bit why we have this discussion and why someone say, okay, this is a very non-problem voting theory. We have infinitely many voting rules. Just pick your favorite voting rule that satisfies some of the actions that you hear. You know, you cannot satisfy all of those concurrently. Just satisfy the one that satisfies that. Just pick the one that satisfies the actions that you want and call it a day. Why do we have a discussion? So the main challenge when we're talking about these applications of voting rules in RLHF comes from the assumption that you cannot just output any ranking, because you want to have a reward model that induces this ranking. So we have the very important underlying assumption that essentially what we want to output is not just get any input and output any ranking that you like, but this ranking should be inducible by some parameter vector theta. And why do you want this? Because you want to be able to generalize. Because in practice, what we are going to do is we're going to get a few candidates, a few samples. We will try to find the parameter vector theta that induces the desired ranking. And then we hope to use this linear model over new prompt analysis that we haven't seen. Otherwise, essentially, we should come up with a ranking over all possible prompt answers, which is, of course, impossible. So that's why it is really important to try to find the parameter vector theta that has some nice properties here. And so probably this, at first glance, doesn't seem so restricted, but I just have an example here to convince you that it's actually quite restricted. So imagine that you have this embedding. So you have 5 different candidates and you are in a 3-dimensional metric space. And so this is the embedding of the different options. And what you want to do is imagine that you want to choose a parameter vector theta such that when you get the dot product of the parameter vector theta and any of the candidates and the vector of any of the candidates, I want the ranking that I'm getting to be A, B, C, D. Assume that this is what I want to do. Why I want to do that? Because given my preferences that I see on my input, I decide that, okay, if I apply this voting rule that has these nice properties, this is the ranking that I want to get. In this case, it is easier essentially to see that there is no parameter vector theta that induces this ranking, because, for example, if I want theta 1 to be above theta 2, from the embedding if I want A to be above B from the bending that I have where A is given by 20, 0, and B is given from 0, 20, 0, and so on. Essentially, I need the property that theta1 is larger than theta2. So if I want to design a parameter vector theta that uses A is above B, if you just do simple math, just shows that I should have the property that theta1 is larger than theta2. Similarly, if I want B above C, then I need theta2 to be above theta3. Just take the dot product, take the condition, and you will see that this is true. And then if I want D to be above E, what I need is theta3 to be larger than theta1, and so there's no way to satisfy all of them concurrently. So essentially, this means that there's no parameter vector theta that really gives me this, satisfies all these constraints concurrently and really gives me this ranking. Yes.
But wouldn't this be solved if you don't use a linear model?
So in general, yes, as long as you go and it's something much more complicated, that is true. But then when you have much more complicated things, then essentially you usually use the generalization property. So if you're going to be able to show some guarantees with respect to generalization, your model should stay relatively simple, and then you see that you have this kind of problems. Okay. So essentially, we saw that this ranking is not in our output domain, and even essentially, if you're going to have a voting rule that it says, okay, this is the ranking that I want, essentially, you cannot really have this. Okay, we call this inner rank aggregation rules, which means that now we don't want just aggregation rules that given the ordinal preferences output an ordinal preference, but instead we want to ensure that what they output can be induced from a linear model. Okay, and so as I said, what we want to see today, so our goal is twofold. First, we want to see what axioms or what properties are satisfied by practices that by approaches that are applied in practice. So, for example, I mentioned to you before that the very common approach is that people assume that the preferences come from the Bradley-Terry model, and then given the preferences that they see, they just apply a maximum likelihood estimator, and this is the parameter vector theta that they find. And so a reasonable question is, okay, if we just ignore that we have heterogeneous preferences, and if we indeed get this approach, what properties do we have? Is it still that it happens to be a good voting rule? So I'm going to answer this question, and essentially I'm going to show some very bad news about the approaches that are used in practice. And then we will also try as a proof of concept to ask, okay, if what people do in practice really fails from axiomatic approach, so really what it outputs has bad properties, is it really possible to satisfy multiple axioms concurrently? Or it is just impossible from a theoretical perspective in a worst case analysis? And I'm also going to answer this question, and essentially I'm going to say that yes, actually it's possible to have better approaches, and so probably we need to reconsider how we do this in practice. Okay, so let me start from the first question. So as I said, there are multiple axioms that people have defined the social choice theory. So this is a more complicated axiom that we consider in our paper. But what I really want to focus in this talk is in this Pareto optimality axiom, which this is a very, very natural axiom, which is what we said before. That if everybody unanimously, everybody in the society says that A is better than B, then our reward model should agree with that. The reward model should not return B is above A. So this is the very, very basic property that someone would expect a reward model to have. And essentially, this Pareto optimality property is violated by any reasonable voting rule that people have defined in social choice theory. So it is a very, very minimal requirement that almost, if not all, almost all voting rules satisfy. So the question is, does this approach of having Bradley-Terry and then taking maximum likelihood estimator satisfy this property, this very, very minimal property? So to answer this question, we actually focused in a more general family of rules, which we call loss-based rules. So this also contains the approach of Bradley-Terry and taking the maximum likelihood estimator, but actually we prove this result for more general loss functions, not only for the loss function of Bradley-Terry. And so here, if you plug in this particular loss function, you are back to Bradley-Terry, but actually we ask this question for more general loss functions. And essentially, informally, what we saw is that as long as the loss function satisfies some very minimal properties, that is either non-decreasing and weakly convex or strictly convex, and this is properties that are satisfied by the Bradley-Terry model, essentially there are cases where what you learn satisfies the very minimal property of Pareto optimality. So what this says is that what people do in practice, where they just try, when they have a linear model, they try to apply just maximum likelihood estimator by assuming the Bradley-Terry model. Essentially, you lose this very, very basic property of Pareto optimality, which says that if everybody agrees that A is better than B, then the parameter vector theta that you learn from this model might output B is better than A, which is probably a signal that we should really account for the heterogeneous preferences. And by making the assumption that what you see is noisy estimators of the random utility model, probably can really ruin things, even in the most basic properties. Okay, and then we turn to the second question, which was, okay, but is it the case that actually you cannot satisfy in some cases Pareto optimality with some other actions? Or is it the case that actually you can have better approaches and you don't? And as I said, the question is going to be that actually you can have better approaches. So then we saw just some rules that if someone applies, can get some nice axiomatic guarantees. I'm going to show you how we did that. I'm not going to claim that this is what someone should do in practice. We don't make this claim. We just say that this is a proof of concept, then you can do something better and you don't. And so for doing that, we turn our attention to what is known as social choice-based rules. So essentially, we went back to social choice theory, and we consider famous voting rules that people have defined, like plurality that I mentioned before, for DAO. There are some other known rules that is Kemeny voting rule. Copland is another one that we define here. And we said that, as I showed you before, indeed, these rules satisfy many actions concurrently. So for each rule, people have studied what are the actions that these rules satisfy. And so if we were able just to output any ranking that we want and get a parameter vector theta that induces this ranking, the problem was done. But the problem is that you have an output domain where the output domain is essentially the rankings that are induced for a particular parameter vector theta. And in your output domain, you might don't have the ranking that you want to output. And so the question is what you do in this case. So we came with a mechanism here, and essentially we saw that, okay, let's say that you want to get a voting rule that is called Copland. I'm not going to define what is this rule. It is a very famous rule, a quite old famous rule that we know satisfies some nice properties. And let's say that Copland indicates that this is the ranking that we want to output. But then we realize that actually there's no way, there's no parameter vector theta that gives this ranking. And so what are we going to do? How are we going to choose a parameter vector theta here that has some nice properties? So what we did is essentially, we try to do a mapping from this ideal ranking to a ranking that is in the output domain. And why to do we try to do the mapping in a way that on our way we preserve all the nice properties that we want. So we don't do the mapping just in an arbitrary way, find a ranking here, but we do it in a very careful way. So whatever nice actions are satisfied for Copland are also satisfied from this ranking. Probably we lose some things, but we still maintain most of the properties. And so, and we did this subject to Pareto optimality, which means that here we just see our domain, see the rules, the rankings that satisfy Pareto optimality, and then we start doing the mapping. So I don't want to go into much details how we do the mapping, because as I said, this is just a proof of concept. It's not, we're not telling anyone, go and do this in practice. And yeah, it is essentially a greedy approach where we start from the first position. We try to see whether there exists a ranking where this candidate can appear in the first position. If this is the case, then this is what we put here. If not, we go to the next one and so on. So it is just a greedy approach where one by one try to put the candidates in high positions, in as high positions as possible here. And so by doing this greedy approach, oops, I went a little too fast. If we do this greedy approach, essentially we're able to get this mapping, and Then by doing that, actually we're able to show that this approach satisfies Pareto optimality and another action that I don't want to go into details because it is a little more mathematical and more complex, along with some other natural axioms. So not only the two axioms that are violated by Bradley-Terry model, but actually on top of that some other nice axioms, where, for example, majority consistency is something that I mentioned to you before, which means that if a majority of users believe that a particular candidate is the top one, then that should be the top candidate in the output ranking. Another one is called winner monotonicity, which means that if you have a particular candidate as the top candidate, then when you go to your input, if you just push this candidate in some rankings above, this should not hurt their chances to be the winner. So yeah, again, in any case, I don't want to focus too much. Someone can try to consider other actions from social choice theory and try to see whether they can be satisfied. But here, really, the takeaway is that what we apply in practice really violates basic axioms, but in fact, there are ways to satisfy these axioms along with some other, and so we might need to reconsider how we're doing things. Okay, any questions about this result?
I have one general question because you said we are not suggesting, I mean, we are not proposing this. I'm curious why.
Yeah, so it's not like we're saying it is a stupid thing to do, no way. But we don't want to claim that, okay, we came up with a great algorithm and this is what we want to do. We really want to claim that we have a proof of concept that indicates that it is possible. Now, how you're going to do, probably people that do more experimental work, they can come with better ideas. But we just want to say that when you look things, we want to indicate that when you look things from a theoretical perspective, we really need to reconsider what we do. But yeah, it's not like I have a particular drawback in mind about this rule. I'm saying that's the reason that you should not apply. No, that's not the case. It is just I don't want to overclaim something. Okay, there are no other questions. I would also like to talk for another work. So yeah, okay. And also the rule that I described actually can be done polynomial time because probably of the way that we do the mapping is not very clear. This kind of thing. Okay, so far we have really talked about heterogeneous preferences and we really have talked how we can really find one reward model that satisfies and how we can really design one reward model given the heterogeneous preferences. However, we claimed in a work that we published this year at NeurIPS that probably this is not even what we want to do. Probably you don't want to have just one reward function for everyone, but instead you want to start having multiple or an ensemble of reward functions here. And then here again is the question, how are you going to design an ensemble and what properties you want your ensemble to have? So this is, again, a joint work with a subset of the previous co-authors. And as I said, it got in the NeurIPS this year. So Itai will be at NeurIPS to present it. So if you're around, you can go and talk to him. You have a question?
Yeah, sorry. Are we assuming that the rankings are linear as well? Like themselves?
Here, no.
No.
Yeah, here we don't make this assumption.
But in the previous one, yes.
Yes, in the previous, yes. In the previous, everything was based on the linear reward function, but here we don't make this assumption.
Not a linear reward function, but linear ranking. Like if A is as much better than B is than C.
Oh, yeah, transitivity, you mean? Yes. So we have the transitivity property. So
that like A could be like way better than B and B slightly better than C.
Yes, this can happen, but we don't make any such assumptions. The only assumption we make is that the rankings come from a linear model, so induced by a reward function that is linear. And so we have the transitivity, so it cannot be that A is better than B, B is better than C, and C is better than A. It's a ranking, but we don't make any other assumptions about the gaps of rewards or anything. Okay, yes.
Sorry. So I was thinking, like, here the main objective is to align in the best possible way the output of the LLM and the human feedback, right?
Yes.
So like, let's think that we have, let's suppose that we have the best potential possible model to align those two feedbacks, those two outputs. will be a potential problem the fact that the human feedback could have or usually have biases or like potential. This could lead to potential unfairness of the LLM because we are trying to align the LLM with the human feedback. So
Yeah.
like
Yeah, definitely I agree with that. Definitely in some cases, probably some bias from human come into play when you design the reward function. Essentially, that's where you have then other ways to try to de-bias your algorithm. So here we just focus on, okay, if let's say that you want to align your model in a way that the society wants, this is the way that you do, but then I totally agree that the next step should be, okay, if actually there exists bias in the human feedback, how can you de-bias that? So yeah, I definitely agree with that. But the main idea of AI alignment is that what we get you want to align with the human feedback, what you see. So that's the main idea. And yeah, it's a second step how you do this. But actually, this work touches a little bit on what you're saying because as you will see soon, we define what it means something to be an outlier opinion, which means that if something is a very extreme opinion, we don't want to get into account. So we go more to a more average user. And so we hope that the more average user, it's not very biased. Yeah, we don't make any claims that the more average user is more biased and so, but we try to not overfit to extreme options. Like if there is a user that asks an LLM, the classic example that if there exists a user that asks an LLM, show me how to build a bomb, the LLM does not do that if the rest of the society agrees that we don't want to do that. Okay, and yes, so as I said, in general, so far we have assumed that we want to design just one reward function, but probably a better idea is not to design just one reward function, is to design an ensemble of reward functions given the heterogeneous preferences. So what this means, for example, here instead of having just one, so okay, if you see this particular example, we have that two people say A is above B, B is above C, so this ranking A, B, C, and one person says that B is above A, above C. And so are there any reasonable definition that someone can come with here? It is clear that this is what you're going to output. So essentially, you're going to go with the majority here. That the majority agrees that A is better than B is better than C. So this is going to be your reward. But this means that you completely ignore 1/3 of the population. So here, okay, I have just one person, but imagine this 1/3 of the population and 2/3 of the population. So you really ignore this minority voice. And there's nothing that you can do about this. So here we ask, okay, if we want to have an ensemble of reward functions, how do we get the voices of minorities as well into account? And so, for example, here, instead of output just a reward model that induces A above B above C, we want to output a reward model also that has the ranking of the last person. And so now it is the question, okay, how do you make things fair with respect to both minority and majority? And so here is, for example, we could say that, okay, because 2/3 of the population believe that A is above B is above C, and 1/3 of the population believes that B is above A is above C, then you can say, okay, that I have this ensemble, and 2/3 of my time I sample from here, 1/3 of my time I sample from here. Or in general, how you do this in inference time, there are different ways. Probably you can do a clustering and you can say that this is the reward function that I'm using for these people, this is the reward function I'm using for that person. But the main takeaway here is the main contribution we want to make here is that we don't want to design just one reward function, we want to design an ensemble of reward functions. And now the question is, how do you design the ensemble in a fair way? And so also to give you some context in social choice theory, and in particular in the field of computational social choice, nowadays, I would say the last 5 years or so, people have really done a lot of works on defining the notion that is known as proportional representation, which means that if you have different people saying different things, you make sure that you are proportionally fair to how many people agree on something or not. So for example, if 1/3 of the population says something, you make sure that 1/3 of the times you agree with them, and 2/3 of the times you agree with something else. So they are very rigorous definition, but the definition that we'll see today is quite simple. Okay, so what is the property that we consider in this work? We consider the property that is called pairwise calibrated ensembles. So we wanted ensembles that are pairwise calibrated. So what is the modeling that we have here is we assume that we show to the users two different options, and then we learn what is the probability someone to say A versus B. So here we assume that we have pairwise comparisons. We don't extend to full rankings. There exists an ongoing work that I'm trying to extend this in full rankings. I'm happy to talk about this later. But in this work, we just consider pairwise comparisons. And given these pairwise comparisons, essentially, what you can learn is that if you have users and you draw a user uniformly from another line population, you learn what is the probability someone indicates that answer Y1 is better than Y2 given some prompt X. So in the previous case, for example, here we had, okay, what is the probability A to be above B? The probability is 2/3. Well, the probability B above A is 1/3, according to the distribution over the different rewards. Okay, and so essentially what we're saying here is that we try to map this as much as possible. So if 70% of the people believe that Y1 is better than Y2, then 70% of the times you want to have it. So you want to design an ensemble that maps this probability. And so here the goal is to have an ensemble of k-reward functions, and in each reward function you're going to give some weight, and so you want at the end your probability of some reward function to indicate that the reward of Y1 is larger than the reward of Y2. When you draw a reward function from this weighted ensemble, you want these probabilities to be as balanced as possible. And this is what we call pairwise calibrated ensemble. So yeah, and as I said, the question, okay, you learn this ensemble, what do you do with that? So there exists a paper, position paper that answers this question for us before us, where they say that, okay, when you have this ensemble, you can use this ensemble in different ways. For example, you can draw from the distribution, for each random user, you can draw from the distribution and then give them the answer with some probability. You can steer the answer, which means that you can return to the user all the different answers. So you get a reward function. For each reward function, you have an ideal answer, and so you return to the user to all of those, or you just return an answer that combines all of those, and so on. There are different approaches. So this idea of ensemble, we're not the first one that we come with this idea. People have thought about it and have even suggested how you're going to implement it. Our job here was like, when you have these heterogeneous preferences, how you design this ensemble in a rigorous way to satisfy different properties that we want, and in particular, the pairwise calibration that we wanted to satisfy here. And yeah, so as I said, one thing that we wanted to satisfy was pairwise calibration, but we wanted also our ensemble to have some other nice properties. For example, we wanted to make sure that the ensemble has a few reward functions, so it's not really very large, because then you go closer to representation and personalization, and then it's much more expensive to maintain things. So we really want to have a few reward functions. We don't want to have, because to some extent, each reward function corresponds to a different foundational model, and so you can imagine that you cannot have a million versions of this. It's very expensive. And we also wanted to exclude, as I said before, what we call outliers, which means views that are extremes, meaning that if everybody agrees that A is better than B, and if everybody agrees that the optimal ranking is A, B, C, and there exists one person that says C is better than B is better than A, then probably you consider this as an outlier, so you want to exclude it from your ensemble. Yeah, we defined it very rigorously what it means to be an outlier. I don't want to go into much detail, but that's the intuition of what we defined. And so we had some theoretical results here. So we saw that in general, pairwise calibrated ensemble, when it has very large size, it is very easy to satisfy. And actually it is as easy as, just do complete personalization. So in this case, easily you can have pairwise calibration because you just learn the reward for each person. You just draw a reward uniformly at random. You're pairwise calibrated as easy as that. But as I said, this is not what you want to do. But instead, you want to have an ensemble with small size. So in general, we saw that it is an NP-hard problem to design an ensemble that satisfies the property that you want. But then we saw some approximation results. So we defined something that is called epsilon pairwise calibration, and we're able to show that with high probability you can satisfy a good approximation of pairwise calibration. Again, I don't want to go into much detail, but yeah, essentially, as epsilon gets smaller, it's more difficult to have it, but then you're closer to pairwise calibration. And yeah, we also have a result. We saw that you can have some approximation with respect to pairwise calibration, and this approximation also defines what is your approximation with respect to your outliers. So how do you exclude your outliers? Yeah, I don't want to stick too much in the theory here. Again, theory serves as a proof of concept that this is something you can do. You cannot do this in polynomial time, but you can have a good approximation. And then we also did, okay, yes, and then we have some results with respect to how you can learn this, and so some complexity results, how many queries you need for learning this. Yes, you have.
Yeah, do we care in practice if we can do it in polynomial time or not?
Yeah, that's a good question. I think in general, people in practice are happy with approximations. So that's why we have this approximation here. And essentially, we saw that, okay, with high probability, if you get a few samples, then you're good. You don't need to do much more things. And to my understanding, this is what people usually do in practice. Now, whether in practice we care about NP-hard results or no, it really depends on how large your problem is. So in this case, because I think the number of parameters can be really huge, probably it's impossible even if you have some very powerful GPUs to do this very fast. Okay, and then we also did some experiments with some real data that are available online. And so essentially here, what we wanted to see is how large the ensemble should be for having a good pairwise calibration. And so here, what you see these numbers is the size of the ensemble, which means how many different reward models you learn. And what I want you to focus here is how fast we move from something that is not a very good approximation of pairwise calibration. So this is how many errors we can have with respect to pairwise calibration, how fast you move on having almost perfect calibration or much lower loss of calibration by just having a few ensembles. So instead of learning just one reward model, by learning 4, 6, you're doing much better with respect to pairwise calibration. And while it is an NP-hard problem, we don't know what is the optimal value of K, because that's also a very important question. Okay, you say you want a small ensemble. How small should it be? There's no clear theoretical answer here, but our experiments indicate that just a few ensembles are enough for going to good pairwise calibration.
What exactly are you measuring here on the y-axis?
So here, essentially, we measure how much you disagree with different pairs. So for each pair, we see how many people say A versus B, so you learn this probability. And when you design a weighted ensemble, you want to see how far away these two values are. So if, let's say, 0.7 people say A is better than B, if your ensemble indicates 0.6, then you're far away by 0.1. And this is the average over all the different pairs. So how far away these two values are.
Okay. In the Reddit scenario, because it's the closest to a use case that I might be more familiar with. But so let's say that you have 2 Reddit users and they rank differently A and B, right?
Yeah.
And then you take the proportion of all these preferences across all the users.
Yes.
And it's 70 versus 30, as you said.
Yes.
And then with your model, you build this ensemble of n reward functions, right?
Yes.
And then you use this reward function.
Then you put also some weights into the different ensembles.
Okay.
So you have a distribution. So let me go back to this slide. So you learn this, what is the probability y1 to be better than y2? And then this is your ensemble, and then you have the probability of y1 be above y2 based on your ensemble, which is defined as I'm getting a reward from this distribution, given the weight. And then what is the probability that this is going to be larger, the reward for y1 is larger than the reward of y2. So essentially, you're just looking at the reward that you sample, you see whether y1 is better than y2, and then you get over the distribution that you have constructed. And you want these two to be as close as possible. And this is the error that essentially we measure. We get the difference of these two over all the different pairs, and so we get the average.
Okay. So I'm trying to also to imagine that one of the first slides where you have the reinforcement learning feedback.
Yes.
So you don't use these reward functions in the LLM pipeline yet?
Yes.
Okay.
So essentially, these reward functions are going to correspond to some policies.
I see.
And then we have some results where we show how these policies also have some nice properties, but all our analysis is based on the reward level.
So you approximate the reward functions from real data with the reward functions that you built.
Exactly.
Okay.
Exactly.
Good, because I'm guessing it's NP hard to achieve pairwise calibration. That's why we're trying to get as close as possible. That's the goal. Right?
So yeah, in general, we know that you cannot be very close. I think the experiments in this particular case was mostly on showing that you really can do good with respect to pairwise calibrations when you have just a small number of ensembles. So here, in general, we saw that given K, the problem is NP hard, but it's also the question, okay, how large K really should be for have good pairwise calibration? Because, for example, if it happens to be, you really need if let's say you have million of users and you really need many hundreds of thousands of reward functions for being pairwise calibrated, then probably it's not very practical. But here we saw that even when we have a very small number of ensembles, we can do much better than just having one ensemble. And so much better is according to this approximation. Yeah.
I have a question about, so if you vary the level of homogeneity in your preference list that you have, and like, so if you make it very homogeneous, does that have an effect on like your final ensemble? Do you have to like have a lower size? Is it correct to assume that?
Yeah, so we didn't really do any experiments with synthetic data to see what happens when the preferences are very, very heterogeneous. Probably that's an interesting question. But I think the problem is that when you have a profile, some preferences that are really heterogeneous and really you cannot see any consensus, then it is very difficult to really, you will perceive most of the inputs as outliers, so you will not really do many things. So I think here really the takeaway is like, if you have a group of users with similar preferences, how are you going to grouping them in a way that they get what they deserve to get? So it's more like a clustering, because if they really disagree, there are not many things that you can do.
Oh, so in the plots, I'm seeing that the line is saying single reward limit, but that's like lower than the one model ensemble. Yes, so here single reward limit means how much you can achieve yes, okay. What we did here is that we imagine that we have the perfect reward model that tries to be just one, that tries to be pairwise calibrated, and here we took the unrealistic assumption that the reward model is not even transitive, just tries to meet the probabilities as much as possible. So with one reward model, you want to say that if so many people say A above B, you try to match it as much as possible. And still we saw that even if you have this unrealistic single reward model, you can really go below what you can achieve with this reward model that you can have by just having a few ensembles.
Gotcha. Yeah. Do you think the progression of the graphs correlates with the number of annotators and the preference pairs? Should you adjust your ensemble size to the number of annotators, for example? Like, should they correspond to each other?
Yeah, I guess from our graphs, we didn't see a very clear correlation of the number of annotators per pair and the size of ensemble we want to have. I think in general, we just noticed that, for example, I think that was the database that had the most not homogeneity. So people really disagree on that. And so it was much more difficult to have something better. While there were a few, like, for example, I think this one was already a lot of agreement on how people prefer A versus B, so it was easier. But yeah, I don't think we came into any conclusion on the number of annotators and the number of ensembles, because we just did the same experiment for all the different databases up to 8 ensembles. I wanted to see how this drops.
But so your ensemble should not like simulate the annotator pool, basically.
No, so we want the size of the ensemble to be completely independent of the population that you have. So even if you have 1 million people versus, I don't know, a few thousands or a few hundreds, you hope that the ensemble that you have is good enough even with very few reward functions.
How much is your data on annotator demographics and those kind of features? And do you account for those variables? Or is it just latently?
So in general, in RLHF, the human annotator state are not available. Usually it is just an ID. And usually, even if the same annotator has answer for different pairwise, even that in some cases not available. So yeah, I don't think that we have any information about demographic data here.
And once you come up with a reward model for a certain choice, does this reward model apply to other choices that they may make down the lane? Or so let's say they're choosing A, B, C for a particular decision. Let's say it's a political candidate. Mm-hmm. Does this say extend to other issues or other rankings? How does that affect?
So how we build our sampling the experiments is that first we choose one reward model, and then we fix that, we choose a second one, then we fix this two, we choose a third one, and so on. I'm not sure if this is your question.
No, so this is about choice, right? So they're making a choice on a particular topic.
Yeah.
Does the reward model, which is designed for a certain topic, apply to other topics?
I see. Yeah, I think these databases are for particular topics, but I'm not even sure what consistency means here, because I guess for different topics you might have completely different answers. Yeah. So yeah, I'm not sure if people have seen, like, especially natural language model, I think it's very difficult to compare to identical answers for a particular topic, because probably the answer is for a particular topic so does not even reply for another particular topic.
No, my thought was, does it make certain inferences about the person making the choices and assume that it would make a certain choice on another topic?
I see. Yeah. I think in general here, when you want to learn a reward function, this is what you try to do. Yeah. Like taking some samples, learn the reward function from the person, and then you'll be able to generalize. So that's why you have either a neural network or a linear model. So yeah, this is what people try to do, just with a few samples to learn the reward model. And there are a few theoretical works that show what is a sample complexity and so on. From an experimental perspective, I'm not sure whether really people have tested this, whether what you learn from a few samples really corresponds to what people would say. But I think in general, because people try to build these reward functions, and there are multiple applications that they have tried to do that, like the moral machine example, where they just try to learn the moral values of the people by a few samples. Yeah, I believe that, yeah, there is some experimental work.
The only reason I ask is you would have to build multiple reward models for multiple choices that you make.
Yeah. No, I think in general we assume that people have some intrinsic reward functions, and given the embedding that you have, they are extendable in all topics. Okay, and yeah, I wanted also, so yeah, that was the main takeaway from this work. I also wanted to mention that in my lab, we have also done some work on what human feedback we want to get to learn the different reward functions, whether pairwise comparisons is better, or whether we want, for example, to get a feedback improvement, because, for example, we might return a particular answer to a user and we ask them to refine the answer. And in some cases, we saw that taking improvement feedback is much better than pairwise comparisons. So there we've done some work on this. And yeah, with that, I just want to conclude, and I want to just give the main takeaways, which is that probably we really need to reconsider how we do RLHF in practice, and probably we need to account for them, heterogeneous preferences. And in general, I'm very excited on this idea of having an ensemble-free word model. So not just to have one model or just to personalize, have something in between. And I think there are many interesting questions here. And with that, I'd like to thank you very much.
Cool. We asked a lot of questions too, in case you guys want to have additional questions for Evi, please go ahead.
Thank you, Evi. I think this was extremely interesting. The fact that everybody was involved is a demonstration of that. Thank you so much for coming here and stopping by. I think in the afternoon you have a rich schedule of one-on-one meetings, so maybe it's time for a break and we can go to lunch somewhere. Any other questions or comments?